All right. How you guys doing? Doing all right? I hear whispers of homeworks and things. It seems to be that time of the semester, right? And a few of you maybe started the homework. Um, all right. So today we're going to finish up the chemistry overview. I didn't quite get through that, but hopefully for any of you that are feeling already overly confident, maybe this will be a good reminder of chemical equilibria instead of just the very basics. Then we're going to get into kind of the core principles of drinking water treatment, just a big picture overview of what we care about, why we care about it. And we'll probably have a little time to begin the derivation of the basis for sedimentation. So when we think about how to treat water, the simplest thing to do would be to use gravity if we can, right? And so that's our first step. So we're going to do a little bit of chemistry, a little bit of big picture. Okay, drinking water, why do we care about it? Kind of obvious. And then get into sedimentation. All right, so if you haven't, grab that. And this week I'm going to, like I've told you, begin populating my roster now that the roster should be, nobody's dropping or adding anymore. So if you do have any issues, please do let me know. We'll get that taken care of. All right. So with that, we're going to pick up about where we left off. Last time we were talking about this problem. And we were kind of just doing an example of converting mass to moles to mass given some relationship. And just as a reminder, the real key here was what is the ratio of one molecule reacting with a particular other molecule. That's typically what we need to know in order to solve some sort of chemistry problem, is what is that ratio. In this case, we were comparing how many carbons in CO2 versus carbons in butane to kind of arrive at our the destination for that problem. Okay, so for equilibrium reactions, the one piece of chemistry that there's a chance you didn't really see much of this in Gen Chem. So we're gonna talk about equilibrium reactions in the sense that they are reversible. They can go one way, but they can also come back the other way. So it's a bit of a two-way street. Many chemical reactions that we look at, like the combustion reaction, we would describe as one way or irreversible, because once you burn this butane, it's simply thermodynamically impossible to come back and form butane from CO2 directly. It's just not something that's going to happen. However, there are some reactions that are a little bit more ambivalent, let's say. For example, chlorine, and you have a problem on this. HOCl is what we think of when we think of household bleach. This is our free active chlorine. It happens to be in equilibrium two forms of chlorine. In fact, the kind you'd have in your household would be more so in the OCl minus. So this equilibrium reaction occurs because you can add a proton, the H, we call it a proton, add a hydrogen, to this molecule, or it can lose one. And it's pretty happy to do so. In fact, there are many reactions like this that we would call an acid-base reaction, where a proton, if it's a very acidic solution, there's many, many protons around, so it's more likely that you've added protons, added these hydrogens, to whatever molecule you're talking about. So this is why pH will affect our chlorination. So the acidity of our solution is going to affect how well our chlorine works, because it turns out this H+, it's going to push the reaction to the left, or if we don't have much at all, it'll kind of pull the reaction to the right to try to release a little bit more into solution. So we're going to talk about how we describe that balance with math and a couple of important scenarios. It looks to be working, but have